All right, there's part two, P.11b. So now we should have an idea of in behavior a little bit how we understand that the degree and the leading coefficient determine where the arrows are pointed. So our goal, again, there's three things that we need to do, and I want to go over exactly how we're going to do those. So again, the first thing with our in behavior, we're going to use the degree and the leading coefficient to determine in behavior, state the number of terms, and eventually we're going to draw a rough sketch. So here we have our chart from the P11 video, and that chart's going to help us walk through exactly how to determine our in behavior. So again, it really relies on the degree. Is it even or odd? And is the leading coefficient positive or negative? So one more time, just to make sure that we're on the same page. In behavior, what am I looking for? I need to know, is the degree even or odd? And then I need to know if the leading coefficient, so the leading coefficient is positive or negative. And once I've determined that, then I can look at my chart and figure out exactly which way the arrows are pointed. Now, as far as the number of turns are concerned, we saw earlier, in fact, we'll just get to that part when we get to it. So the first things first, let's determine in behavior, okay? So a few examples on in behavior. The first one, we have f of x equals x to the fifth plus 3x to the fourth minus 2x plus 1. All right, well, my degree here is 5, and my leading coefficient is 1. All right, so the degree in this instance is odd, so I know this is going to be odd. My leading coefficient is positive. So I go to my chart. The degree here is odd. Leading coefficient is positive. So I know that the arrow on the left is going to be pointed down and the arrow on the right is going to be pointed up. And remember, we have a fancy way of writing that. So for this problem, since the degree is odd, leading coefficient is 1, we're going to say as x approaches negative infinity, remember this is to the left, comma, then the y values, f of x, the y values, f of x, approach positive infinity, right? So as x approaches negative infinity, f of x approaches positive infinity. Notice these little arrows here, the word I'm using for the arrows is approach. The reason why we have to say approach is that no number will ever equal infinity, right? You can't equal infinity because if you equal infinity, there's a number bigger than infinity, which is still infinity. It's crazy to think. So that's why we have to say approach, right? So as x approaches the negative infinity, right, we're going to the left. The y values are going up. No, excuse me. I just messed up big time. We said the degree was odd and the leading coefficient was positive. The y values are going down. Come on, Stevens, get your head in the game, son. This is going to be negative. We have a negative infinity here. I'm sorry about that. Now, on the right side, the arrow is pointed up, right? So then we could say as x approaches positive infinity to the right, then the y values are going to be going up. That is true. Some of you are going to hate me for that, and that's okay. All right, so now we go to the next one. Everybody's allowed to make mistakes, right? Now let's take a look here. We have the degree on this guy is 2, and our leading coefficient is -1. All right, so the degree is a 2. That's an even number, right? Evens are 2, 4, 6, 8, 10. Odds 1, 3, 5, 7, 9, right? So we have an even degree, a negative coefficient. I go to my chart. I have an even degree. I have a negative coefficient, so I know my arrows are both going to be pointed down. The arrows are both pointed down. So then we could say on the left side, as x approaches negative infinity, f of x is also going to approach negative infinity, right? Both arrows are pointed down. The left arrow is pointed down. And then as x approaches positive infinity, the right arrow is also pointed down. Right? So as x approaches negative infinity to the left, f of x, my y values, are going to negative infinity. They're both pointed down. All right, the next one we have, let's see if we could go by memory on the next two. All right, so the degree here is 3. All right, so that's odd. The leading coefficient is -1. All right, so that's negative. So odd and negative. So that means that my left arrow, so as x approaches negative infinity, my left arrow is pointed up. F of x approaches positive infinity. This time I know I'm right. And as x approaches positive infinity, the right side is pointed down. Right? Remember, when it's odd, the arrows are pointed in different directions. And finally, we have the degree here on this one is a 4. Leading coefficient is a +7. Right? When the degree is even, they're both pointed in the same direction. Positive is up. So here we say, as x approaches negative infinity, then f of x is approaching positive infinity. And as x approaches positive infinity, then f of x is approaching positive infinity. All right, so the left arrow is pointed up, and the right arrow is pointed up. Now let's take a look at number of turns for a second. I want to go back to our graphs that we had on the last video. Here my degree is even. My degree is even. But the degree here is a 2. The number of turns I had was 1. I had 1 turn. So the degree is 2. My turns are 1. Over here, the degree was 3, and my number of turns was 2. Everybody see a pattern developing here? The degree is 4. The number of turns is 3. Anybody see the pattern yet? Here, the degree is 5. The number of turns is 4. And the pattern is going to hold true. The pattern will always hold true when it comes to turns. So the next couple examples, we're going to state the maximum number of turns for the following functions. The maximum number, it could have less. It could have less than the number, except for when the degree is 2, it will always have 1 turn. But when the degree is 3, 4, 5, 6, or 7, it could have less than the maximum number. But the maximum number, the number of turns is always equal to the degree minus 1. So you might see me write this as turns is equal to the degree minus 1. So all we have to do, state the maximum number of turns for these. All right, well, the degree here is 5, and 5 minus 1 is 4. So 4 possible turns. Now, if we haul off and graph this on a calculator or graph this on Desmos, it could have less than 4 turns, but it's going to have a maximum of 4 possible turns. Here we have a degree of 2. Right? 2 minus 1 is 1, so 1 turn. Now, it's a degree of 2. It will always have exactly 1 turn. This one's a little special. Now we go to 3. Here the degree is 3, so this is going to have 2 possible turns. This could have 1 or no turns. That's kind of an interesting one. So graph a whole bunch of third-degree polynomials and you'll see what I mean. All right, here the degree is 4, so this is going to have a max of 3 possible turns. And that's it. There's really nothing more special than that. There's really nothing more special than that. All right, so the last thing we want to do is we want to sketch graphs. So here, this is where we're going to use our knowledge of end behavior and turns and put it together in a very rough sketch. And I'm not even going to use, I don't even want to use a coordinate plane. because I just want to give a very rough, I mean, when I say rough, I just want you to think of the idea of what it could possibly look like. So let's start with this. We know the degree here. The degree is 5, which means that it's odd. The leading coefficient on this guy is a 1. So that means that my left arrow is pointed down, and over here my right arrow is pointed up. And now I know that my number of turns, so 5 minus 1 is going to be 4. So I'm going to try and sneak 4 turns in between. So 1, 2, 3, 4, and connect my arrows. Not a great looking graph, but that's okay. Here I have a 5th degree polynomial. I have 1, 2, 3, 4 turns. Arrow pointed to the left. Arrow left is going down. The right arrow is going up because that follows the odd coefficient, odd degree, positive coefficient. All right, so let's take a look at the next one here. Here we have the degree is 2, leading coefficient is -1, and we have 1 turn. All right, so negative leading coefficient, the degree is 2, so both of my arrows are pointed down. And I know that it has exactly 1 turn. So here all I have to do is make 1 big turn, and I'm done. All right, here on this next one, we see that the degree is 3, again, which is odd. Leading coefficient is -1, so that's negative. Odd and negative. So we can start with that. We know that the left arrow is going to be pointed up. The right arrow is going to be pointed down. And the number of turns on this is going to be 2. So 3 minus 1 is 2. So I make 1, 2 turns and connect my arrows.
Can I get a custodian to 116B to unlock the door, please?
No!
Custodian to 116B to unlock the door.
No custodians to no 1/16. All right, so here the degree we have is 4. Our leading coefficient is +7, which means that both of my arrows are pointed up. I have one arrow going that way, and both arrows are pointed up. And now the number of turns. The degree is 4. 4 minus 1 is 3, so the number of turns is going to be 3. So I'm going to sneak this in here. We have 1, 2, 3 turns, connect my arrows, and boom, I got it.